Okay, good morning everyone. Welcome back. So today I hope to finish chapter 5. So last time we talked about mathematical formulation of nodal pricing, and this is actually an optimization problem. So you need to solve optimal power flow problem. Okay. So we talked about one bus network, and then go to infinite capacity with losses, and then introduce the finite capacity. Did we discuss that yesterday? Monday? Yeah, finite capacity and with losses. So yeah, we stopped it here. And the problem is solving OPF is not easy. The reason is because the optimization is not convex optimization. So the way to solve that is to linearize that. So before we discuss how to linearize it, we need to go to the power flow equation first to describe AC OPF problem, and then we'll discuss DC OPF. Don't be confused that DC OPF does not mean that the network is DC. The network is still AC, okay? But we ignore reactive power and simplify the problem. And because there is no reactive power component, the one who first invented that algorithm called that is a DC power flow. So the terminology is not quite good. It is not DC power flow, but the name is DC power flow because it does not have reactive power. It only considers active power. Okay. So to discuss that, what is power flow? We have here, we have a bus K, generator and load. This bus is connected to bus I and bus J. So power flows like that, power injection and load. Okay. So typically the active power and reactive power, this notation is based on the direction is injection. When this value is positive, that means power is injected into that bus. Okay. So if this is positive, power is injected. Yeah, for generator case, and in the case of load, no, that's the opposite. Okay, so anyway, we can think of the power flow from K to I, that is denoted by PKI, or from K to J, PKJ and QKJ. So actually, this is called power flow equations. You may not familiar with this equation, but just take it. Power systems can be described based on these two equations. This is called power flow equations. So, of course, it would be better to know the transmission line, the transformer, the physical, the things, the electromagnetic theories, blah, blah, blah. But after we model the power system, this is the result. So as long as you understand this power flow equation, then you are ready to solve optimal power flow problem. Okay. So here again, Ki are the bus index, and Vk and Vi are again in power system. This is AC system, so the voltage and current are complex number. So that's why S equals Vi conjugate. This is complex power, complex voltage, and complex current. So each variable has magnitude and phase. But here, this is just the magnitude, different notation. Okay, so the magnitude of voltage at bus K and I. And the theta K, theta I are the angle of voltage at bus Ki. And this G and B, this is the real part of the admittance matrix and the imaginary part of the admittance matrix. So what is the G and B? They are just dictated from the impedance of the line. So when we have two nodes, I and J, we can think of the resistance and the reactance component, so R and X. So the impedance of that line is R plus J X, right? And the inverse of that is denoted by Y. So this is admittance. right? And we can construct admittance matrix, and the admittance matrix is typically denoted by capital Y, and we put minus here, okay, just for linear algebra perspective. And the meaning of YII is just a sum over all J. This is again for just linear algebra perspective. Okay, and then because we have Yij, yeah, this one. So the real part of that is denoted by capital G, and the imaginary part of that is and put minus sign there. So yeah, that is the Bij. Okay, so this Gij Bij is related with this line parameter, impedance or admittance, conductance, subsettance, etc. So anyway, as long as this Gij or Gki, Bki are known, we have variables such as the voltage magnitude at each bus and the phase angle at each bus, and that perfectly describe the power flow of the whole network, right? So the voltage, actually, no, the voltage magnitude and phase angle means, okay, let me put like that to denote this is a complex number. So suppose that we have some kind of network, single line diagram like that. And as long as you know this complex voltage and you know the impedance or admittance of each line, you see how the current flows, right? Voltage difference and current flows. And then the definition of complex power is V times I conjugate. So as long as you can determine this complex voltage, you can describe how the power flows. Okay, so what you need to know is this complex voltage or the voltage magnitude or and phase angle. Okay, so yeah, this is power flow equation. So roughly speaking, the power injection at bus K goes from K to other bus I, depending on the phase angle difference here and there, so cosine and sine. And something like that. Okay. So, yeah, we have these two power flow equations, but if we use this power flow equation, that means we need to solve AC OPF problem, which is non-convex, so hard to solve. So we want to make it simple, and the way to do that is neglect reactive power component. So, of course, we need to solve it, but we neglect it. The reason is because the power factor is very close to 1. Assume that the power factor is close to 1. So active power is dominant than reactive power. Just totally ignore this Q component. We assume Q is 0. Okay, no reactive power. That's why this is called DC power flow. Okay, and also, okay, so after removing this equation, we have this single equation. And we want to make it further simplify. And to do that, we assume that the resistance is 0. Okay, so there is no ohmic loss. And the line only has this reactive component. Okay, so Rij is 0. So when Rij is 0, this Gij is 0. We only have this Bij term. So, yeah, this is further simplified. This part is 0, and that is described like that. Okay, first assumption, no reactive power. Second assumption, resistance is 0. Third assumption, what? The phase angle difference is not that much. Between node I and J, the phase angle are not that different. Okay, that is the third assumption. And when this value is small, the approximation of sine theta is just theta, right? So this is further simplified to Okay. Yeah, there are 4 assumptions. Before going to that part, the voltage magnitude is almost 1.0. Of course, it changes slightly, but the voltage magnitude does not change much. So we assume that they are voltage magnitude, and we are using the per unit notation, normalized one. So they are just 1. Okay. Yeah. Third simplification. And the fourth simplification is this is very small. So instead of using sine, we are just using this term. So after that, finally, the equations we have is just this one. We only consider active power. Okay, we only have this BKI component. We only care about the phase angle difference. Okay, so this is a linear equation. Yeah, because this is an approximation, it is different from what it happens in real system, but this is a good starting point to compute optimal power flow in real network. Because this is easy to solve, it takes much less time. So in reality, the KPX solves DC OPF for more than 1,000 buses in a very short time, using some computation method, the linear algebra method. Okay, so yeah, this is the power flow equation, DC power flow equations. And in your textbook, so up to this point, this is the standard notation in power system analysis. But in your textbook, this part, that part are omitted, and just starts from here. So this is not current. This is just injected power, as we use the notation here. Well, yeah, this I is the net injection. You remember that? So I, where is, yeah, IK is the net injection at bus K. Okay, so in your textbook, the notation is that. So for DC power flow, the equation is this: the phase angle difference, Yij, and I. So the injected power, injected active power at bus K goes to other buses depending on the phase angle difference and this value. Okay. So again, injected power, and you can think of the power flow between node I and J, that is denoted by Fij. So the power flow between I and J is the phase angle difference times this constant. So then the DC OPF problem is that actually, here we do not have objective function, but the objective function is same as before, minimizing the total cost of the network, this one. You remember that? The cost at bus K for the net injection IK, and the constraint is that this is the equality constraint. The total network losses is equal to the total net injection of all the buses, because the power losses should be compensated by the net injection. If there is no losses, net injection is sum of net injection will be 0. But because there are losses, the sum of net injection should be equal to the total losses. This is equality constraint, and we have a Lagrange multiplier pi there. And also, for each line, there is a maximum flow limit. And so FL is the line flow, which is a function of the net injection of all the buses except the slack bus. Okay, so that should be less than FL. So inequality constraint and the Lagrange multiplier for that. So yeah, objective function and equality constraint, inequality constraints, and the variables, optimization variables are theta I, theta j, and Fij is described based on that. Yeah, Actually, in optimization problem, you can think this is also an optimization variable, and we have equality constraint. And this is the inequality constraint. So the Lagrangian function here is our original cost function. And what is it? This is total loss, but in this formulation we do not have total loss term. This is power balance at each node. This one. This one. No, they are variable. This is the net injection at bus I, so they are same. So that is here. And so for each bus I, we have this equality constraint, so pi I. And this is for each line between I and j. We have a maximum power flow limit. So for each ij, we have this Lagrangian multiplier, mu ij. So summation over I and j. Yeah, so this is Lagrangian. And then think about why we do not have this one. Why is that? No, this is about, so why don't we have this term? Originally we had this term, but here we do not have that. Why? 민재. 근주. 힝. Power losses, but in DC power flow, zero resistance, so there is no ohmic loss, right? So there is no loss, so we don't need to care about this. DC power flow, we assume zero resistance. Okay. So this is our Lagrangian, and then the KKT condition is that for each variable, so here the variable is the net injection and the phase angle at each bus, and this is the dual variable. Dual variable Lagrangian multiplier, same thing. Dual variable, another dual variable. So dual variable for equality constraint, dual variable for inequality constraint, and this is the complementary slackness. Okay. Equations. So solving optimization problem is to find a variable that satisfies the KKT condition, right? So this is actually solving optimization problem is to find a solution of some equations, right? And because sometimes you can find the solutions of the KKT conditions with a closed form. For very simple problem, you can do that by handwriting. But in many cases, solving an equation may not be easy, so you need to find that solution using an iterative algorithm, right? So that's why almost all the optimization problem requires iteration. So that's why it is called programming, linear programming, non-linear programming, etc. Okay. Any questions so far? Actually, you need to check it on your own to do your homework. For 3 bus cases. 3 bus case, okay? So, and to solve it, let's think about it. So if there are m binding constraints, what does that mean? We have n equality constraint. This is equality constraint, so this is not called binding constraint. Equality constraint must be met all the time. So binding constraint means that there is inequality constraint and the optimal solution is at the boundary, right? So when there are n binding constraints, that means totally we have how many? Yeah, there are some number of inequality constraints, but there are n binding constraints. Then that means there are n plus 1 marginal generators, and the nodal price at the bus where the marginal generator exists, we can compute that nodal price from this condition. You can compute pi I. Then you can determine n plus 1 nodal price. And so because there are totally n nodes, there are n nodal price. So n minus n plus 1 unknown prices, and that will be determined later. And also because we have m binding inequality constraints, we have non-negative dual variable mu ij for each binding inequality constraint. So, and using this condition, take the derivative with respect to theta I that is 0, then we have this condition, dual variable for equality constraint, dual variable for inequality constraint. Anyway, so we have n minus 1 equations. So you can solve it. Okay, and actually the DC power flow solver solves it. When there are thousands of buses, you need to use some commercialized software. So I don't want to go into the details of this step. So we have a set of buses where the price is known, as I told you already here. And for other buses, we do not know the prices yet. But after you solve this DC OPF, all those variables are determined. Okay, so this is kind of tedious. Check it. And your homework is to solve this simple 3-bus case. You can solve it by your hand. Okay. So in this case, we have again 3 buses and the 4 generators and marginal generators at buses 1 and 3. So known and unknown, and you need to determine what is it. I think this problem is same too as before. 7.5, 10. You are familiar with this number, right? So previously you did something to compute the nodal price here. But in this case, you are using DC power flow. Right? So do that on your own. So yeah, intermediate step. You need to solve it. And finally, you will get this result. So anyway, the answer is in your textbook. So you know the answer, but you need to follow the step to get this answer. That's your homework. Okay. Yeah, so the answer is here. Any questions about the homework? The due is next Monday. Okay? Okay? Yeah, due is next Monday. Okay, then let's talk about the AC modeling. Anyway, we need to solve AC OPF problem because DC power flow only models the flows of active power and it does not model the voltage magnitude. We assume they are just 1 and ignore the constraint of voltage magnitude as well and only considers the active power injection. So because of these inaccuracies, operators ISO, KPX impose conservative limits on line flows. So if you need to operate the power system based on DC OPF solution, this is just an approximated solution and the operator needs to take it as a conservative way. Okay, and because of the inaccuracy, it may hinder market efficiency. However, full AC modeling is not yet feasible, complex, non-convex optimization. So that's why we need to study and develop a better way to do that. Okay, so let's move on to the next topic, the final topic of chapter 5, which is about financial transmission rights. Which is very interesting concept. And this may be confusing to you, but interesting idea. And you need to recall what you learned before, which was about contract for difference in chapter 2. Very simple, so let me remind you again. And the motivation of introducing this financial transmission right is that, actually, what is financial transmission right? When you are a consumer or you are a generator, then you can purchase financial transmission right, and then you can get money depending on the power flow. Okay, so you buy the right to receive money depending on power flow. That's the meaning of financial transmission right. Okay, so the operator sells it at some price, but anyway, as long as you have it, you can get money based on the power flow. Let's see what that is. So why do we need to introduce this new concept, financial transmission right? That is because sometimes congestion happens and sometimes power losses exist. So the nodal price fluctuates over time. And this fluctuating nodal price is kind of uncertainty for generator and the loads. So what was the theme of power system economics in chapter 2? Forward contract, not forward contract, forward contract and future contract. So that is about hedging. Okay, to prepare against the uncertainty, we need to make sure that the price is fixed for seller and buyer. So they are happy about that because they can have a good night's sleep, right? So yeah, conditions and losses affect nodal prices, and because of some other things, anyway, we have uncertainty and the nodal prices changes, it fluctuates. So both generators and consumers, the buyers and sellers, do not want to be exposed to this price uncertainty. So that's why they need to have a financial mechanism to avoid the risk. Okay, so yeah, and that's the motivation. And what was contracts for difference, CFD? Well, very recently you may read the newspaper article, which is about CFD in about something. Well, never mind. Anyway, this contracts for difference means that, so this is about bilateral trading. But why do we need to have this kind of concept? The reason is because all the transactions actually happens in a centralized market, in a centralized way. But when there is only a centralized market, but these two participants, seller and buyer, want to make a bilateral trading, they can have these contracts for difference. So even though the goods are traded at the centralized market at the market price, they can have another contract for this bilateral trading. And they only need to pay or get the difference to realize this bilateral trading at the agreed price. The market price and this agreed bilateral price can be different, of course. Do you see what I'm saying? Okay, centralized market equilibrium, price changes over time. This is another kind of uncertainty. So seller and buyer wants to make a contract for a fixed price, right? But all the transaction happens in the centralized market. So, but they want to secure this transaction at a fixed price. So the way to implement that is just to pay or get money based on the difference between their agreed price and the market system price. I say simple things in a very long way, but anyway, so we have a centralized market. So in this centralized market, producers must sell at their nodal price, which is computed in the system. And the consumers must buy at their nodal price, which is computed from the system. But they agreed on this bilateral trading. So after that, producers and consumers are allowed to enter into bilateral financial contracts using contracts for difference. So let's look at one example. Again, we have Bulgaria and Slovenia. Here, contracts between Bulgaria and Moldavia is that Moldavia steel. So quantity 400 megawatt. Strike price means that the agreed price between the seller and buyer for contracts for difference. Okay. Strike price is $30. So this is fixed. And other participants also trade across the interconnections. And then, so because there are other participants, the nodal price at this bus, at that bus is computed like that, 24.3, okay, no condition in this case. So, but anyway, they made a contract at this strike price. So first, Bulgaria Power sells this much at this price in the market, and Moldavia buys the same amount at the same price, so pays this much, okay? And then the contracts for difference means that Moldavia need to pay more because the agreed price is, the strike price is $30. So this is the difference. So this amount is further to pay to Bulgaria Power, okay? And Bulgaria Power, so the net cost of Moldavia is this plus that. The sum of these two is $12,000. And the Bulgaria Power gets this money from the contract for difference. So the selling price is not 24.3, but actually $30. So yeah, so the net revenue is 12,000. Obvious. So what? So this is contract for difference. Okay. Using a centralized market, they can have bilateral trading at the strike price. But the thing is, the interesting thing happens when there is congestion. So suppose that congestion happens, and the system computes the nodal price, $19 and $35. Okay? But anyway, they have CFD, contract for difference. So, okay, first, this Bulgaria Power sells this amount at that price. This is the revenue. And the Moldavia Steel buys 400 at this nodal price, so pays that much. And because this is contract for difference, the Bulgaria Power expect this much further. They sell it at $19, but they made a contract at $30. So this much should be paid from Moldavia to Bulgaria, right? And Moldavia still expects, well, I made a contract at $30, and but I paid $35. So I need to get money, this much, from Bulgaria Power. What? Yeah, Bulgaria Power expects this money from Moldavia, and Moldavia expects this much from Bulgaria. So there is discrepancy, actually $6,400. So contract for difference does not work under a congestion. So what? So a basic contract for difference breaks down with nodal pricing. So we need to think about the second one is that now the financial transmission rights concept kicks in. So we observe that there exists shortfall in the contract for difference, but when you computed condition surplus here, the condition surplus is what? The buyer to pay minus the sellers, buyers to pay and sellers to get. The difference of that is condition surplus, right? So the buyers paid a lot, but the sellers received small. There is a difference that was called condition surplus. And in this case, the condition surplus is actually exactly this much. Yeah, $16 times 400, this much, right? So the concept of FTR is that the system operators sells financial transmission right to users, and the users who hold this financial transmission right can get money based on this, based on the price difference, the nodal price difference and the power flow. Okay, and actually this is same to condition surplus. So FTR contracts for F megawatt between Voldry and Sildavia entitles the owner the owner of FTR to receive money. So when you have FTR, you can get money based on this condition surplus. But you need to purchase it first. Okay? So the holders of FTR are indifferent about where they trade energy, but just when I have it, when power flows, when the nodal prices are different, I can get money. This what they expect, but if this nodal price is reversed, they may need to pay money. Okay, tricky. And the system operator collects exactly enough money in condition surplus to cover the payment to the holders of FTR. So the condition surplus is collected from the participants and it goes to the one who holds this FTR. So yeah, let's look at this example again. So quantity same, 400 megawatt. The strike price same, $30. And to cover itself against nodal price risk, Voldria Power purchases 400 megawatt of FTR from the system operator. Here we don't know at what price Voldria Power purchased this FTR. Okay? That information is not here. But assuming that, yeah, Voldria Power has FTR, let's see what happens. Voldria Power sells 400 at this much. So this is the revenue. Sildavia Steel, yeah, pay this much. And the system operator collects this different, this amount. This is called condition surplus. And because Voldria Power has the FTR, it receives the money, the power flow times the price difference, this much from the system operator. In this case, they are saying. And then Voldria Power pay, by the way, they have CFD, contracts for difference. So they agreed to transact trade energy 400 megawatt at $30. That's the strike price. So the Voldria Power pays Philadelphia, they buy at $35, but they agreed at $30. So this amount is paid back from here to there, right? Agree? Not quite sure. You are not quite sure. Yeah, initially they have contract for difference, bilateral trading at $30 for 400 megawatt. But no, Philadelphia paid $35. Too much, right? So pay back the difference between the 35 and 30. So this money is paid back from Boldria to Philadelphia to realize contract for difference. Okay. So yeah, then the Philadelphia Steel's net cost is, originally their cost is this much, but this is payback, so $12,000. And the Boldria Power's net revenue is what? So this one plus this one minus 2,000 is this one. So everybody happy. Okay. So it looks good. You agree with that, right? Professor says it looks good. Yeah, it looks good, right? So what's the benefit of the CFD and FTR? We use the congestion surplus to implement bilateral trading at a fixed price using contracts for difference. Okay? So the price does not fluctuate and they are not exposed to the nodal price fluctuation. Okay?
근데 여기서는 저 FTR을 얼마에 샀는지 안 나와 있는데
Yeah.
사실 저 레베뉴에서 그만큼 빼지는 거예요.
So next topic, actually we do not discuss that here, but next topic is how can acquire FTR. Actually anybody can acquire FTR. Boldria Power can have it, or Philadelphia Power can have it, or you can have it. Okay, so FTRs provide a perfect hedge against variations in nodal prices, but because we don't know the real value of FTR, and when we do not know the value of the goods to trade, the best way to do that is to use auction. So auction is kind of resource allocation mechanism. It used a lot in real systems, communication systems. We sell, the government sells the frequency to SKT, KT, LGU plus based on auction. You don't know that. The government does not know the value of the frequency, so use auction. So yeah, again, in this case, FTR, nobody knows exactly how value it is. So based on auction, this FTR is sold. So auction transmission rights for the maximum transmission capacity of the network. And the system operator cannot sell more transmission rights than the amount of power that it can deliver, because if you sell it too much, then the system operator may need to give more money than it sell. Think about it. So if the system operator sells FTR too much, then it may exceed, this may exceed the physical limits. So that may not be good for the operator. So the operator may lose money. Anyway, so the proceeds of auction help cover the investment cost of the transmission network, and users of FTR, so to participate in this auction, the users of FTR must estimate the value of the rights they buy at auction. Okay? And this FTR is defined from point to point, node to node, or bus to bus. And no need for a direct branch connecting directly the points between which the FTRs are defined. No need for a direct branch connecting directly the points between which FTR. Well, yeah, just FTR is defined point to point, okay? And market participants do not need to be concerned about how the power flows from one location to another. You know, that's the job of system operator. And the FTR holders can get money or pay money depending on the power flow and the nodal price. Okay? So, yeah, good. Another example of FTR. You saw this figure many times before. You know, 3 bus, that price, and that price. This is the actually limit binding. I think so. Power flow, right? The maximum power flow here is 126. Maximum power flow here is 66. You did the homework, right? This constraint is not binding, right? Okay. So here, consumer at bus 3 have CFD with generator at bus 1. This is bilateral trading, so 100 megawatt at $8. And the reference price is node 1. And also, this consumer purchased FTR for 100 megawatt from node 1 to node 3. Okay. Settlement. Consumers pay 100 megawatt at $10 because the nodal price at node 3 is 10. So that's right. For extracting 100 megawatt at bus 3. Okay, so even though they have CFD, first the transaction is at the central market, right? So because and this is nodal price. Anyway, this consumer pay 10 times 100. That is here. And the generator collects 100 times 7.5 because the nodal price is 7.5 for injecting this much power at bus 1. And then because they have contract for difference, this consumer pays consumer. The consumer pays this much to the generator because this price is $8, but this is 7.5. So this consumer need to pay this much more price difference, and the consumer's additional payment. But the consumer have FTR, so consumer collects power flow times the price difference. 10 minus 7.5. So this from whom? From system operator, right? So from the system operator, because consumer has this FTR. Then this consumer effectively pays how much? So pays 1,000. Pays 50. And this is revenue, so minus 10,000 plus 50 minus 250 is $800. So which is equivalent to a price of 8. Okay, so in this case, using FTR, the bilateral trading using CFT at this strike price is done. Good. Simultaneous feasibility. The system operator should not sell more FTR than the transmission network can physically handle, and the set of FTRs that it sells must meet the simultaneous feasibility test, because FTR depending on the power flow, and so the system operator cannot sell which violates the physical law of the system. And so if flows corresponding to these FTRs are actually implemented, the system operating limits should be respected. And if this test is not satisfied, the system operator will not collect enough conditions of loss to cover its FTR obligations. Yeah, so the feasibility is important. And so this is not your homework. Let's look at this. Again, no, same as before. This dispatch is feasible and uses the maximum transmission capacity here and here. Okay, yeah. But I remember that original capacity was blah, but it was cut half, something like that. Okay, so in this case, we can think of maximum net feasible injections. So here the maximum, the net injection is 285. Here 60 load. Here net injection is 225 megawatt. Then, because there are 3 lines, you can think of 3 FTRs. Here, 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 depending on the nodal price and the power flows. Right? So the combination A is think about this kind of power flow. Actually, there are a lot of ways to split it using superposition principle. This is one way, satisfy. And this is another way. Looks good. And this is the other way. Right? So for 3 cases, case 1, case A, case B, case C, and from bus to bus, in case A, we have 2 lines. So here, from 1 to 3, 1 to 2, and the power flow amount and the nodal price are already computed. So from bus price to bus price, you can compute the revenue from FTR. So this minus that times this amount. Okay. And this table is filled like that for the case of A, B, C. Okay. And these are settlements for financial contracts, not the physical injection. And these combinations of FTRs use all the available transmission capacity. Assuming using all the transmission capacity, this is the FTR. And the total revenue of FTR for the case A, this much. Case B, case C, they are all same. And then also you can check the condition surplus. For this case, the nodal prices can be computed, and then so consumption and production and nodal price or nodal marginal price computed as before, and consumer's payment, consumption times nodal price, that the producer's revenue, this price times the production, that, and the difference is condition surplus this much. You didn't have your homework yet. Okay, this is obvious, so no homework yet. Okay. So this is equal to the total value of FTRs. Yeah, no. This value 785.50, 785.50, they are saying, interestingly. But let's do something else. Suppose that the capacity of this line is limited by 65 megawatt. Okay, so this is the previous case. We already know all the nodal prices, but the limit is reduced to 65. Then the generation changes from 75 to 77.5, and the nodal price, okay, the injection changes from 50 to 47.5, and nodal price at bus 2 changes from 11.25 to 5. And from these values, you can compute the values of FTRs again for the combination A, B, C. Each case, compute all of this, blah, blah, blah. And sometimes, you observe because of this price is less than that, but power flows like that, so the FTR is negative here. Negative. So that means even if you have FTR, sometimes you need to pay money. Okay. Blah, blah, blah. And these are the values. And so what? So observations. Prices at bus 2 is lower than price at bus 1 and 3 because increasing the load at bus 2 would reduce the cost of congestion. If you increase the load here, when there is a congestion here, this congestion decreases. So when you increase the load, when congestion increases, the nodal price increases, but this is the other way around. If you increase your load, that is good for system operation because that resolves the congestion here, right? So that's why the nodal price at bus 2 is lower than bus 1 and 3. And some of the FTRs have negative value. This means that the owners of these FTRs have to pay the system operator. So what is your homework? Where is your homework? Yeah, that is 1, but homework 2. Where is your homework? Let's see. Now we have another example. In this example, now we are focusing on consumer at bus 2 here. And the consumer at bus 2 has CFD with generator 1, and the strike price is $8. The quantity is 60 megawatt. And also, the consumer 2 purchased FTR for 60 megawatt from node 1 to 2. Okay? And let's see what happens. Settlement. Consumer pays 60 times 5. The reason is because so 60 times 5, the payment of cost consumer, $300. The generator collects 60 times 7.5 because nodal price is that. And because they have CFD, the consumers pay this much further, the price difference, 7.5, but they agreed on $8. So this much is paid from consumer to the generator to settle the contract for difference. And the consumers pays this much to the system operator because it has FTR. So that's not good for the consumer. Am I correct? Yeah, it has a FTR here, right? So, and consumer does pays a total. Yeah, this plus that's $480, which is equivalent to $8 strike price for 60 megawatt. Again, they are same. Interestingly, you are not quite sure why, but interesting, right? But another interesting thing is that when you compute the congestion surplus, this case, load, generation, price, dollar to generators, dollar from loads, net then we have that value, and what is it? Actually the value of FTR was this much, 412.50, but in this case, when you computed all of these things, the congestion surplus is that much. They are different, so that is less than this value, the value of FTR. And why is that? The reason is because when we computed this, we assume maximum capacity for each branch. This revenue is computed the maximum the possible maximum, not maximum. Actually, these are these numbers. Then, because the system operator was not able to deliver the full transmission capacity that it assumed when it sold the FTR. So the power flow of this is different from this one. The generation, the amount has changed, and it was also changed. Right? Where is it? Yeah, the generation changes. It has changed. So something has changed. So when it sold FTR, but the system has changed. So yeah, because the system operator was not able to deliver the full transmission capacity that it assumed when it sold the FTR, that is less than the total value of FTR. Okay. So now you know, okay, FTR looks interesting, and it plays a role when congestion happens to realize bilateral trading using contract for difference. But there are also some problems with FTR. There are many possible point-to-point transmission rights, and it is difficult to assess the value of all possible rights. And it is difficult to set up a market for point-to-point transmission rights. So this is something that can sell. This is something that can be sold, or there is a market for this, for trade FTR. But designing that kind of market may not be easy. So yeah, this is the last topic. This is called flow gate rights, not FTR, FGR. And the idea here is that, again, what is FTR? That is to reduce the price fluctuation due to congestion, right? But actually, not all the lines are congested. Only a few of them are congested. So we do not need to care about all the lines for FTR. We only need to care about the lines that can be congested. So the observation is typically only a small number of branches are congested. So by the concept of FGR, flow gate right, is that by transmission rights only on those lines that are congested. And the advantage of that is the fewer rights need to be traded. We don't need to make a good for each line. If it is not congested at all, then we do not have that kind of concept. But the difficulty is that, yeah, it is not easy to identify the branches that are likely to be congested. Okay. So actually, this I don't want to talk about. I don't want to talk about it more. But FGR is actually based on solving OPF again. So because to identify the branch that will be congested, right? So as long as we can solve OPF, we can do that. But no, that's not easy. So fewer in FGR. So fewer potentially congested line than point-to-point combination of FTR. But it is hard to predict the value of point-to-point FTR, hard to predict when a particular line will be congested. Must understand operation of the network when dealing with this FGR. No, must understand operation means no, need to solve ACOPF. Oh, this is the last slide. Do you think so? Oh, is it? Okay. So you have only one problem. Good for you. I will see you next Monday. Any questions today? I'm pretty happy to finish chapter 5 today. And we will move on to chapter 6 next Monday. Thank you.